Hi, everybody. We are finally on our last lesson of the school year, which is just nuts to think about, right? Little recap of, or a little preview of what's going to happen the next 2 weeks. We'll review tomorrow, take our final test of the year, and then we will review for our actual final, like the semester final, the rest of the time we're together, okay? Please be good for the sub. It's very difficult to sub at the end of the year because everyone's kind of stir crazy. So just be on your best behavior. If you finish your worksheet early, please work on anything that you're missing or just find something quietly to do at your desk, okay? But this lesson today is going to feel really similar to what we did at the end of last chapter. So last chapter we had congruent and similar figures, but now they're three-dimensional, so they're solid. So again, one's going to be big, one's going to be small, and we'll just learn some properties about them. So let's just get some words down here. So similar solids have the exact same shape, but not necessarily the same size. Their linear measures, such as height or radii, have equal ratios. And remember that ratio that we enlarge it or shrink it by is called the scale factor. So all of this information up here, you guys, isn't new. That's stuff we had learned at the end of last chapter. A congruent solid is the exact same shape and the same size. So our first little bit here, we're just deciding if these pyramids or these solids are similar, congruent, or neither. And if they are, what's their scale factor? So we just have to match, right? Here's the height of this pyramid. It matches with the height of the bigger one. So 4/6. Get it as a decimal or reduce. That would reduce us to 2/3. All right. Now we're going to match our edge lengths. So 8 and 12. 8/12. That also reduces to 2/3. So since we got the same scale factor for our linear measures, they would be similar. And they want us to list the scale factor. It doesn't give us an order, but I think on your homework I say do it from the left to the right. So our one on the left is a smaller one, so 2/3. But since it didn't specify, you could have put 3/2 if you wanted. All right, another one here. We have a couple of cylinders. Let's see here. So it looks like our diameter on the small one is 6.2. And then they're telling us our diameter on the bigger one is 6.2. That reduces to 1/1. And then if we look at the height, 6.8/6.8, that also reduces to 1/1. So when two solids have a scale factor of 1:1, they are congruent because they are the exact same. Your scale factor is 1:1. All right, nothing nuts there. Now we have a little exploratory thing to help us kind of figure out what are these properties that these similar solids might have. So we have two cubes here. We need to find their scale factor, the ratio of their areas or surface areas, that means the same thing, and the ratio of their volumes. So let's start with the scale factor. We're just matching, right? 3/2, can't reduce it, that's what it is. Now, surface area, you guys remember finding all the different sides, the areas of the sides, and adding it up, right? So a cube, that's pretty simple because all your sides are the same. So if I'm looking at this cube, it's 3/3, and we have 6 of them. So 3 times 3 times 6 is 54. Similarly with our smaller cube here, 2 times 2, and there's 6 of those. So our surface area is 24. So if we write our ratio of our surface areas, 54/24 reduces to 9/4. Okay. Now we have the ratio of our volumes. So we're going to have base area 3 times 3 times the height of our cube, which is 3. So that's 27. And then with our smaller one, 2 times 2 for our base area times its height of 2. That gives us 8. So the ratio of our volumes is 27/8. So now we're just kind of looking, right? Is there anything special that we notice? Well, let's label here. Our scale factor and our ratio of our areas. We should know something about that from last chapter, right? Like if I call this A/B to get to the ratio of our areas, we know we do a squared over b squared. But is there any connection between our scale factor and the ratio of our volumes? And maybe if you're like a math nerd or a number person, you can kind of see these things maybe a little bit more easily than someone who's not. But hopefully you're making the connection that from your scale factor to the ratio of your volumes, we're just cubing it. So it's a cubed over b cubed. Because 3 times 3 times 3 is 27. 2 times 2 times 2 is 8. So the big takeaway from today is our scale factor, we'll call it a to b. To get to the ratio of your areas, we square it. Again, that's nothing new. We learned that last chapter. The new piece here is the ratio of our volumes is a cubed to b cubed. Okay, so now we're just going to do some problems solving for either missing measures or volumes or surface areas, okay? It says the edge of a small cube measures 4 centimeters. If the scale factor between the small cube and the large cube is 1/3, what is the surface area of the large cube? Okay, so just be organized in your work and you'll be okay. So it says the edge of a small cube is 4 centimeters, and we have our scale factor is 1/3. And we want to eventually get to the surface area of the large cube. Maybe give yourself a visual. Here's a cube. I'm just going to do it 2-dimensionally because it's just easier for me. The edge of our small one's 4. And we have its surface area. We're looking for the surface area of our large one, okay? So, our little roadmap here, right? What do we know? Well, we know our scale factor is 1/3. And now we got to get to the ratio of our areas. Remember, how do we do that? We square our scale factor. So 1 squared over 3 squared equals 1/9. And then from there, we can write a proportion, right? And then we write our proportion. So we're going to have 1/9 equals, do we know the surface area of our small one? As of right now, we don't, but since it's a cube, it's pretty easy to figure out, right? So it's going to be 4 times 4, and there's 6 sides, so times 6. So 4 times 4 times 6 gives us 96. So our surface area of our smaller cube is 96, and we're looking for the surface area of the larger one. And remember, you match up these numbers based on what these numbers are, right? So the top was my smaller one, so that's why I put the surface area of my smaller one on top. Now we just cross multiply. So we're going to have x equals 9 times 96 is 864. Centimeters squared. Okay, next one. 2 similar rectangular prisms with square bases have surface areas of 98 square centimeters and 18 square centimeters. If one base edge of the larger rectangular prism measures 9 centimeters, what's the perimeter of one base of the smaller one? So this is kind of like a loaded question, right? There's kind of a lot going on. So let's just break down what we know of both rectangular prisms. We have both of their surface areas, right? So let's start with the ratio of our areas, the surface areas. I like to always put the small one on top, so it's easier for me to reduce. So 18 over 98. That reduces to what, you guys? 9 over 49. Now we're looking for the perimeter of the smaller prism, right? So that's going to be based off our scale factor. So now I need to go from the ratio of our areas to our scale factor. So remember from last chapter, right now we're at a squared to b squared. We have to take the square root. So the square root of 9 is 3. The square root of 49 is 7. And then from there, we can write our proportion. So we're going to have 3 over 7 equals. But now what does it equal? Do I know the perimeter of my bigger prism? I don't, but I do know that the larger rectangular prism has a base edge of 9. So if there's 9 on one and it's a square base, what's the perimeter of this larger one? 9 plus 9 plus 9 is 36. So now I can finish my proportion. We're looking for the perimeter of the smaller base, and we know the perimeter of the larger one's 36. And then we just simply cross multiply. So 7x equals 3 times 36, which is 108. Divide out, and we should get 15.4 centimeters. Okay, finally have a picture on this one. Maybe that's more helpful. It says a rectangular prism A and rectangular prism B are similar. Find the volume of rectangular prism B. Okay, so we gotta draw our little road map. Can we start with right away? Well, I can clearly see that 2 goes with 4, right? So we're gonna start with our scale factor, which is 2 over 4. I'm gonna reduce it because I want my number smaller, so I know it's a scale factor of 1/2. Then from here, I need to get to the ratio of our volumes. So what do we do to our scale factor to get to the ratio of our volumes? We cube them. So 1 cubed is 1, 2 cubed is 8. And then lastly, folks, we have to write our proportion. So we're going to have 1 over 8 equals, we're looking for the volume of the smaller prism, right? Do I know the volume of the larger one? No, but we can find it, right? Base area, 4 times 6 times the height. And that gives us 192. So now that, since that was our larger one, that goes on the bottom. Put x on top, and now we solve. So we'll have 8x equals 192. Divide out, x equals 24 inches cubed. Two cylinders are similar. The ratio of the radii is 3 to 2. The volume of the smaller cylinder is 60 cubic inches. Find the volume of the larger one. Okay, if it helps you, give yourself a little visual. 1 cylinder, 2 cylinders. The ratio of the radii is 3 to 2, so this is 3, this is 2. And then it tells us the volume of the smaller cylinder is 60, so volume equals 60. And we're looking for the volume of the bigger one. All right, so where do we start? Hoping you're thinking we're starting at the scale factor. I'm gonna put my smaller one on top, do what you wanna do, 2 over 3, doesn't reduce. Get to the ratio of your volume, so what do you do to your scale factor to get to the ratio of your volumes? We cube them. So we're gonna have 2 cubed, 2 times 2 times 2 is 8. 3 cubed, 3 times 3 times 3 is 27. And then from there, we can write our proportion. So we're gonna have 8 over 27 equals, we know the volume of the smaller one, 60, throw it over x. Now we cross multiply. So we'll have 8x equals 27 times 60 is 1620. Then divide by 8, and we should get 202.5, our units, inches cubed. Okay, now these last two folks, it looks like we're working backwards from the volumes, okay? So we're kind of going in reverse order. Says the containers at the right are similar cylinders. Find the height h of the smaller container. So do you guys see how this time we're looking for h, but we know both of our volumes. So this time we're starting at the ratio of our volumes. So again, I'm going to put my smaller one on top. So 270 pi over 640 pi. And this is where you really do want to reduce, you guys, because they will almost always give you numbers that simplify nicely. Okay, our pi's cancel. Our zeros cancel. Can we reduce 27 over 64? Nope. So that's the ratio of our volumes. And now we have to get to our scale factor. So now we're going from a cubed to b cubed to just a over b. So when we do that, we have to take the cubed root. I think some of you have done this in class, but I'll show you if you have a calculator like the ones that are in my classroom, how you do that. So if we wanted to find the cubed root of 27, you're going to hit 3, and then you're going to hit the second button. And then from there, folks, you're going to hit the up arrow right here. So now it should be 3 with a little X star with this radical symbol on your calculator. Something that kind of looks like this right now. And now you type in your number 27. So 3. So that should have given us 3. Now let's try 64. I'm just going to walk you through it one more time. If you know how to do this, awesome. Then ignore me. Oops. So again, what we do there, we're going to hit the button 3 because I want the cubed root. The second key, this up arrow. So again, it should be 3x like this. And then you type in 64 and you should get out 4. Okay. And then from there, you write your proportion. So we'll have 3 over 4 equals, we don't know what h is on the small one, over 10. Now we just simply cross multiply. So 4h equals 30. Divide out, h is 7.5 inches. Just inches, because it's linear. Okay. Last one. The world's largest puzzle cube has an edge length of 1.57 meters. The ratio of the edge length of the largest puzzle cube to the regular cube is approximately 27.5 to 1. Find the surface area of the regular puzzle cube to the nearest hundredth. Okay, so this is our scale factor right here, right? And so we know our scale factor is 27.5 to 1. And they want us to find the surface area of the regular puzzle cube. Okay, so then we need to get to the ratio of our areas. So again, what do? From our scale factor to the ratio of our areas, we square them. So 27.5 squared is 756.3. 1 squared is just 1. And then we write our proportion. So we have 756.3 over 1 is equal to, but what does it equal, you guys? Do we know the surface area of either of them? No, but we can find the surface area of the big one, right? If we have a cube that has a length of 1.57 multiplied by its height to find the surface area of one side. So 1.57 times 1.57 multiplied by 6 for the total amount of sides. We should be getting 14.8. Does that sound right? I don't know. Let's check it real quick. Yep, we're going with it. 14.8. So that's the surface area of the world's largest Rubik's Cube, and we're looking for the surface area of the smaller one. So again, we'll cross multiply here. So we'll have 14.8 equals 756.3x. Divide out, and yes, you're going to have the small number on top. So 14.8 divided by 756.3. X is equal to 0.02 meters squared. Whew. I understand this is not an ideal time for me to be gone. It's not an ideal lesson for me to teach via video lesson. Try your best. Please be good for the sub. We will fix all the things that are wrong tomorrow when I'm back.